All right, welcome to the deep dive. Today we're going to be diving into something that's pretty fundamental. I mean, it gets to the heart of how we understand reality. We're talking about continuity and infinitesimals.
Yeah, this is one of those topics that really gets the philosophical gears turning, doesn't it? Are we living in a world that's ultimately smooth and connected, or is everything ultimately made up of discrete, indivisible little bits?
It's a question that's been haunting philosophers and mathematicians for, well, literally millennia. And for this deep dive, we've gone deep. We've explored ancient Greek texts, medieval treatises, and even cutting-edge modern mathematics.
And what's fascinating is, along the way, we've seen how certain ideas that seem to have been settled long ago have actually resurfaced in some really unexpected ways.
It's almost as if history is forcing us to reconsider some of our most basic assumptions about, well, the nature of reality itself. So in this deep dive, we're going to try to unearth some of the most intriguing insights and key developments in how people have understood continuity and these mysterious infinitesimals.
And we'll try to do it in a way that resonates with anyone who loves to grapple with those really big, fundamental philosophical questions.
Exactly. Okay, so to start this off, let's rewind the clock way back. We're talking ancient Greece, right?
Yeah.
Where do we first encounter these ideas?
Well, one of the earliest hints of something like infinitesimals pops up in the work of the atomist philosopher Democritus around 450 BCE.
Ah, Democritus, the atom guy.
Exactly. And the heart of atomism, of course, is that matter and extension space itself can't be divided forever. You eventually get to these fundamental, indivisible particles, the atoms.
So it's a profoundly discrete view of the world. Everything's built from these tiny, separate building blocks.
Precisely. And this idea wasn't just about physical matter, it also influenced how they thought about mathematics. But this view faced some pushback. By about 350 BCE, Eudoxus, a really influential mathematician, basically excluded infinitesimals from what would become the official Euclidean mathematics.
So a move towards a more rigorous system, maybe hinting at a preference for continuous magnitudes.
Yeah, something like that. Now, fast forward many centuries to the late 19th century, and we find Charles Sanders Peirce, the American philosopher.
Pierce, yeah, he was a big thinker.
Oh, absolutely. Peirce coined the term cynicism. It was a central idea in his whole philosophical system. Cynicism emphasizes connectedness, the idea that continuity is a fundamental aspect of reality.
So the opposite of atomism, in a way. Things are fundamentally linked, not separated.
Exactly. For our purposes, think of cynicism as the direct opposite of atomism. Now, we'll also come across the term divisionism, which specifically refers to the idea that continua are infinitely divisible.
Okay, so we've got atomism emphasizing the discrete and cynicism highlighting the continuous. So where does Aristotle, a towering figure in Western philosophy, fit into this picture?
Well, Aristotle was a staunch cynicist. He argued that physical reality is what he called a plenum, a completely filled space. So for him, the continuum of space, time, and motion, that wasn't something you could break down into simpler, discrete parts. It was irreducible.
So no fundamental building blocks for Aristotle.
Right. Now, his view of infinite divisibility is especially interesting philosophically. He believed that continua are potentially divisible infinitely. You can always keep dividing in principle. But he insisted they can't be actually divided into an infinite number of parts all at once.
That's a subtle distinction. Potential versus actual infinity. How did he use that to address those early philosophical puzzles about continuity, like Zeno's paradoxes?
Right, you're talking about the famous paradoxes of motion, like the dichotomy paradox.
Mhm.
To travel any distance, you've got to first travel half of it, then half of that remaining distance, and so on. It creates this infinite series of steps.
It makes motion seem impossible.
Exactly. And then there's the Achilles paradox, where swift Achilles can never overtake the tortoise with a head start. Achilles always has to first reach the tortoise's previous position, but by then the tortoise has moved a bit further. Aristotle's concept of potential infinity let him argue that, sure, you can keep dividing the distance forever, but you never need to actually complete an infinite number of divisions to traverse the distance.
So motion is continuous and real, and Zeno's paradoxes come from a misunderstanding of how potential infinity works in a continuous reality.
That was his take anyway. Now, it's fascinating to compare Aristotle's cynicism with Epicurus, who came a bit later. Epicurus was a materialist, so he had different philosophical commitments, and Aristotle's idea of potential infinity didn't really work for him.
So back to atoms.
In a way, yeah. Epicurus felt he needed to posit actual physical atoms, but he ran into Aristotle's arguments against continua being made of dimensionless
Right,
points.
points are just locations. They don't have any size.
Exactly. So Epicurus tried to modify atomism. He proposed that these atoms, although indivisible, still had conceptually indivisible parts that did have extension. They took up space.
So extended but fundamentally partless. A sort of hybrid approach, trying to reconcile the discrete nature of atoms with the apparent continuity of the world.
Exactly. He was wrestling with the same fundamental problem, just from a different philosophical angle. Aristotle had shown how a continuous magnitude can't just be built from points, which lack extension. So Epicurus's response was to suggest indivisible units that weren't just mathematical points, but had a minimal, irreducible size.
Okay, so we've got this fascinating back and forth playing out. Let's fast forward now through the centuries to the medieval and early modern periods. What happened to these ideas of continuity and infinitesimals?
Well, in medieval Europe, Aristotelian thought was dominant, which meant most thinkers rejected the idea of continuum and of indivisibles. But there was a new wrinkle, and it came from theology.
Religion enters the picture.
Right. Scholastic thinkers were wrestling with the concept of God's infinity. This created some tension with Aristotle's idea that infinity exists only potentially. Some started to wonder if actual infinity might exist outside of God, maybe in the seemingly infinite points on a line.
So now the nature of infinity, both divine and mathematical, got all tangled up.
Exactly. And we see some thinkers, like Henry of Harclay and Nicholas of Autrecourt, reviving forms of atomism, echoing Epicurus. They tried to argue against Aristotle, but there was a strong Cynicist counter-movement, too. One of the big figures was John Duns Scotus. He came up with some ingenious geometrical arguments against continuas being made of indivisibles.
Geometrical arguments.
Yeah, for example, he argued that if you could make the diagonal inside of a square from indivisible points, not only would they have to be commensurable, but they'd be equal in length.
That's a big no-no in geometry, right?
Right. And that goes against Euclid's proof that they're not commensurable. Scotus also argued that if two unequal circles with the same center were made of indivisible points, part of an angle of the larger circle would equal the whole angle of the smaller circle. Again, this violated basic geometry.
So those arguments have a very visual, intuitive quality.
Yeah, very clear and powerful. William of Ockham, another big name, also weighed in. He focused on the infinite divisibility of the continuum and emphasized density.
Density, meaning
Density is the idea that between any 2 points on a line, you can always find another point. Ockham distinguished a tree continuum, where parts form a real unity, from a mere collection of separate things, what he called a contiguum. While he didn't explicitly say a line is made of points, he had this brilliant insight. A punctate yet continuous line might be possible if you imagine it as a dense array of points rather than points in simple succession.
so not just points next to each other, but points packed infinitely close together.
Right. It really foreshadows later developments in understanding the real number line. Now, in the 14th century, Thomas Bradwardian took on the challenge of refuting atomism. In his Tractatus de Continuo, he aimed to show that continua can't be made of indivisibles. He laid down basic principles about continua and showed that the atomistic view led to contradictions.
A systematic takedown of atomism.
Precisely. Later, Nicholas Cusanus offered a different perspective. He embraced actual infinity. He said any continuum, whether geometric, perceptual, or physical, can be divided in two ways. You have an ideal division that goes on infinitely and an actual division that stops at atoms.
So two kinds of division.
Right. Cusanus also famously envisioned a circle as a regular polygon with an infinite number of sides, all infinitely small.
That image of a curve as an infinite-sided polygon comes up a lot when people try to grapple with the infinitesimal.
Absolutely. And this brings us to the early modern period where things started to shift. The focus moved away from the metaphysical nature of indivisibles to their practical use in the emerging field of calculus. The 16th and 17th centuries saw calculus really take off.
And calculus is all about continuous change, right?
Right. You can see it as a sort of synthesis of the continuous and the discrete. And infinitesimals played this crucial role, bridging the two. The question became less about what are they and more about what can we do with them.
So from being to doing.
Exactly. Thinkers like Johannes Kepler used infinitesimals a lot in his work on calculating volumes. He imagined curves as polygons with an infinite number of sides, and solids as made up of infinitely many tiny cones or disks. He even introduced the idea of a mathematical object continuously changing. Galileo also leaned towards atomism in a mathematical sense. He thought continuous magnitudes were made of an infinite number of indivisibles.
Infinitely many, infinitely small parts.
Right, and he famously came up with this thought experiment where you bend a line into a circle, suggesting a curve could be understood as infinitely many infinitesimal straight lines.
That image is so powerful, even if it's logically a bit shaky.
Definitely. Now, Galileo's student, Bonaventura Cavalieri, made infinitesimals into a more reliable mathematical tool. His method of indivisibles was a breakthrough. He saw surfaces as made of parallel lines and volumes as made of parallel planes. What was important was the correspondence between these indivisibles, not their exact number. His method basically reduced the dimensions of a problem, making it easier to solve.
So while these early mathematicians were getting amazing results with infinitesimals, their logical basis was still a bit iffy.
Yeah, Berkeley famously called them ghosts of departed quantities. Then, in the 19th century, mathematicians like Cantor and Russell really went after infinitesimals. Cantor called them cholera bacilli, infecting math, and Russell thought they were unnecessary, erroneous, and self-contradictory. The 19th century saw a big push to get rid of them and replace them with the rigorous concept of limits. This was the era of making the continuum all about numbers.
The time of epsilon delta proofs and a quest for absolute rigor.
Exactly. Infinitesimals didn't completely vanish, though. Physicists and engineers kept using them because they were so intuitive and helpful. Some differential geometers found them useful too, so they went underground in a sense.
So a powerful idea that refused to die. But wait, there's more. The story takes an amazing turn, right?
Oh, absolutely. In the last few decades, we've seen something truly remarkable. The concept of the infinitesimal has been brought back, but this time with a rigorous foundation.
Hold on. They found a way to make infinitesimals mathematically legitimate.
They did. It's happened in a couple of different ways. First, there's Abraham Robinson's non-standard analysis, which he developed in the 1960s. Using mathematical logic, Robinson created a system that includes the standard real numbers, but also has infinitely large and infinitesimal numbers. Amazingly, the usual rules of arithmetic still work in the system.
So infinitesimals that behave like regular numbers.
In essence, yeah. And an infinitely large number in this system is bigger than any standard whole number. And its reciprocal is an infinitesimal, a number that's not zero, but smaller than any positive real number.
So a logically consistent framework for these slippery little quantities.
Exactly. Non-standard analysis also has this really cool feature called the transfer principle. Basically, it lets you take statements that are true for standard real numbers and, under certain conditions, translate them into true statements about this extended system with infinitesimals. And this leads to simpler, more intuitive proofs of some classic theorems in analysis.
So a whole new way of thinking about calculus. And you mentioned there's another approach.
Yes, there's smooth infinitesimal analysis, or SIA. This is a different beast altogether. It doesn't focus on infinitesimal numbers, but rather on infinitesimal magnitudes.
Infinitesimal magnitudes.
Yeah, and it's built on a particular set of axioms. The most important one is the principle of microfineness. This principle says that any function defined on nil-square infinitesimals is affine, which means linear.
Wait, nil-square infinitesimals, what are those?
A nil-square infinitesimal is a number that, when you square it, you get zero, but it's not zero itself.
So not zero, but it squares zero. That's strange.
It does go against our normal intuition about numbers, doesn't it? Now let's call the set of these nil-square infinitesimals delta. What the principle of microfineness is saying is that within this infinitesimally small neighborhood, any function acts like a straight line. You can't bend or break delta. You can only slide it around or rotate it, and this has a crazy consequence. In SIA, every function from the real numbers to the real numbers is continuous.
Wow, every function is continuous. That's a huge difference from standard analysis, where we have lots of functions that aren't continuous.
Absolutely. Another key principle in SIA is microcancellation. This gives you a way to handle these infinitesimals. And from the principle of microfineness, you can actually derive Fermat's rule about stationary points. But here's another mind-bender. The logic behind SIA isn't classical logic, it's intuitionistic logic.
Oh, so we have to change the rules of logic to make this kind of infinitesimal work.
Yeah, that's crucial. It's been proven that SIA's axioms don't work with the law of excluded middle. The mathematical structures that make SIA work are called smoothed poses, which make sure SIA is consistent with intuitionistic logic. This link to intuitionism is really interesting philosophically. It ties SIA to constructivist views of math.
What an incredible journey. From the ancient Greeks arguing about indivisible atoms to these super sophisticated and logically sound frameworks like non-standard analysis and smooth infinitesimal analysis. It's clear that the whole debate about discrete versus continuous and the role of infinitesimals has been a constant theme in both math and philosophy.
Absolutely. And we've seen how different people have understood the continuum throughout history. Sometimes it's seen as something fundamental, sometimes as potentially made of indivisible parts, or as a densely ordered set of points, or even as a product of our own intuition. And then there's SIA, where it's like a smooth fabric at the infinitesimal level. And infinitesimals, after being banished from math, have made this amazing comeback, offering new and potentially more intuitive ways to think about the very foundations of mathematics, and maybe even the structure of reality itself.
So for our listeners out there, all the philosophy fans, what's the big takeaway from all of this?
Well, I think it shows how dynamic and ever-changing even our most basic concepts are. Our ideas about continuity and divisibility have gone through huge transformations over time. The fact that this debate is still going strong and that infinitesimals have been brought back from the dead tells us there's no one definitive answer to whether reality is ultimately discrete or continuous.
So many different ways to see the world.
Exactly. All these different frameworks we've talked about, from atomism and cynicism to non-standard analysis, intuitionism, and SIA, they each give us a different lens to look at the world and how we represent it mathematically. They challenge our deepest intuitions about space, time, number, and even infinity itself.
So dear listener, it really makes you think, doesn't it? Which of these views of continuity resonates most with you? Do you lean towards the discrete building blocks of atomism? Or maybe the interconnectedness of cynicism? Perhaps the rigorous infinitesimals of non-standard analysis are more your style, giving you that powerful mathematical tool. Or do you find yourself drawn to intuitionism, where the continuum is built from mental constructions? And then there's SIA, with its strained, smooth, locally linear world. Which one feels most right for understanding the fundamental structure of reality? And what does that choice mean for how you understand change, motion, and the very fabric of existence? These are big questions, and they're still driving both math and philosophy today. If you want to go even deeper into these ideas, the Stanford Encyclopedia of Philosophy is a great resource. It was a key source for our discussion today. And with that, we'll wrap up this deep dive. Thanks for joining us.